Mercedes? One of the good.
Yeah, that's fine.
You wouldn't think there'd
That's
be a
fine.
dog
Go right ahead.
Okay.
Yep.
Well, Mercedes even.
We're starting again.
Okay. Well, thank you for the invitation to be here. I have spoken on this subject actually a fair number of times because I really got interested in climate science when I was teaching analytical chemistry at Lebanon Valley. And particularly, I was interested in the infrared absorbing properties of the gases in the atmosphere. So that sort of got me going. And then I got a little bit upset, increasingly upset by all the denial and the sort of the assault on the science, that it's junk science, fake science, etc. So back in the, around 2010 or so, I decided, well, I'd try to put together something that covers the science for an everyday audience, not for scientists. And to sort of give them the sense that this really is a serious endeavor, this study of climate. And because otherwise, the denialism tries to undermine it. And then that undermines also progress and interaction. So anyway, that's where I'm coming from. So, but it's been a while now since I've given my last talk, so I had to go back and update a whole bunch of data, which had changed. But I want to start out approaching climate change from a planetary perspective. And so that's why I have a picture of planet Earth, which is suspended in space. And space is a rather inhospitable place to be. And among other things, it's a perfect vacuum, almost perfect vacuum, which means that it's also an almost perfect insulator. And so therefore, for Earth to receive energy or to give off energy, it can only occur through radiation, through light. So let me go on to the next slide. Oops, went the wrong way. Okay, so every hour, the Earth absorbs energy from the sun. Enough energy in 1 hour to power all human activities on Earth for an entire year. That's a lot of energy coming from the sun. And if the Earth couldn't lose that energy, it would rather quickly become uninhabitable. First uninhabitable, then way beyond uninhabitable. But it does have a mechanism for releasing energy. So there's radiation coming from the sun to add energy, then there's radiation from the Earth to release that energy. We can't see that, that second type, but if we could, the second type of radiation that Earth uses to cool is in the infrared region. If we could see it, it would look something like that. The planet, from all angles and at all times, emitting warmth out into space. So what we have then is these two sort of competing processes. We have energy coming from the sun that warms the Earth, but that can't go on too long. And then we have energy that the Earth emits, and these are very different. This is visible light, this is infrared radiation. And the Earth system will always try to achieve energy balance of those two processes. So if the sun energy were to drop, then we have less coming in, more going out. Then the energy going out would drop, but at a lower temperature now to achieve a new balance. So the Earth is always working to achieve energy balance for the system. They call it actually top of atmosphere, because if you were up there with a magical spaceship and could see the energy flows, you could see the balance. However, the radiation coming from the light isn't quite as simple as the previous slide, the energy coming from the sun, because some of it actually is reflected and doesn't make it to the Earth. So things like ice, snow, sand, clouds, and aerosols, very fine particles that are suspended in space. These reflect some of sun's radiation back, but about 70% makes it through and warms the atmosphere and the surface. And we have satellites. I have a thing here, I think I'm we have satellites that have been orbiting the Earth for decades now. The NASA SOURCE mission measures continuously as it goes around the Earth the incoming solar radiation. And the NASA CERES experiment measures both the cooling radiation that the Earth sends out and also reflected. So we understand these very well, the radiation. And I think the key finding here is that the radiation measured coming from the sun has been almost perfectly rock solid without changing for the past 5 decades. The only change is in the last decade where it's dropped a little bit, but just a tiny bit. Okay, now the other key thing here is the idea of the greenhouse effect and greenhouse gases. And I'm going to give you a way to think about this. It's a oversimplification, but the real thing is way beyond anything we really want to delve into. But this is pretty much gives you a pretty good idea. So the greenhouse gases are gases in the atmosphere that are trace gases, tiny, tiny amounts of the atmosphere. And they absorb the radiation that the Earth is giving off, hold it momentarily, then re-emit it, send it out again. Sometimes sending it out at one angle, sometimes directly back, sometimes space. The net effect is then that some of that radiation then is sent back to Earth. So the Earth is sending out infrared radiation to cool, but then the greenhouse gases send some of it back. Now these are absolutely critically important to life on Earth. If we had an atmosphere with no greenhouse gases, just oxygen and nitrogen, which are the big components, if we had that, the average temperature on Earth would be about 0 degrees Fahrenheit, 32 degrees below the freezing point of water. Without these greenhouse gases, we couldn't have life on Earth. Life as we know it anyway wouldn't have developed, and it wouldn't be sustainable. So greenhouse gases are a good thing. But you know what they say, too much of a good thing. So, and what are these greenhouse gases then? Well, here are the 4 key greenhouse gases that affect warming, global warming, greenhouse effect on Earth today. 3 of these are naturally occurring. They've been in the atmosphere for millions of years. Carbon dioxide, methane, nitrous oxide. The last one here is actually a grouping of maybe 40, 50 different molecules. What they have in common is they all have the element fluorine. Okay, and these are man-made, and they've only been in the atmosphere for 40, 50 years. Okay. Now, all of these have really low levels in the atmosphere. Carbon dioxide is overwhelming the most prevalent one, but it's only 0.04% of the atmosphere. 0.04%. We express that as parts per million, but it's the same thing. Methane is 200-fold less, and methane is what we call natural gas. Okay? We drill for it. Nitrous oxide is 1,000-fold less, and these fluorinated ones are 1,000,000-fold less than carbon dioxide. Okay, Okay, so there's not many of these things at all, and that's what a lot of people early on in climate denial said. How can something that tiny affect the entire planet? Well, it affected the planet enough so that life could develop and be sustained. So when these things are emitted into the atmosphere, carbon dioxide and fluorinated gases are there for a long time. Hundreds of years, millennia. Methane, half is gone in 9 years, another half's gone in another 9 years, etc. So these two, if these two have to be replenished or are replenished. And carbon dioxide is eventually removed by photosynthesis, but it just takes a while. Now the key thing here is global warming potential. All of these interact with the cooling radiation and send it back to Earth. It's just that some are better than others. Carbon dioxide is the worst in the bunch. We'll give it a relative value of 1. Methane is 30 times more effective at absorbing cooling radiation and sending it back. Nitrous oxide, 273. And these fluorinated things are just unbelievable. There's one that is 23,500 times more effective than carbon dioxide. It's called sulfur hexafluoride. It's used in the electric grid as an insulator for electric switching, and they use thousands of pounds of this. And so 1 pound of that gas gives the same warming as 23,500 pounds of carbon monoxide. Now, as far as how these affect the temperature of the Earth, it depends on the potential and the amount, sort of a product of those two. Okay. Carbon dioxide has the lowest potential, but it has the highest amount. And you can see this in the next table here. These are contributions of these gases to warming in the USA and in the total world. So in the USA, about 79% of all warming, of all greenhouse effect, comes from CO2. 11.5% from methane. 6% from nitrous oxide. And these fluorine gases, even though they're a millionfold less than carbon dioxide, they crept up to 3%, and they're in the atmosphere for the long term, believe me, the long term. Worldwide, it's a little bit different. There's more methane produced. This is largely from agriculture, but also from drilling for oil and other things that escapes. Okay, and there's a new thing here, carbon dioxide. This carbon dioxide comes mainly from burning fossil fuels and from industrial processes, as here. But with the world as a whole, there's a lot of forests being cleared and being burned, and that produces additional. So that's burning current carbon. Fossil fuels is burning ancient. So you can see there's a difference, a little bit less in the fluorine gases. But, so all of these are contributing. And I would expect, for example, to see that this slice of pie gets smaller. But I'm a little bit concerned about this slice of the pie, because they're so powerful as greenhouse gases. Okay, now, carbon dioxide has, this is roughly almost a million years, last million years. Carbon dioxide has seesawed quite a bit through various ice ages and warmer periods, but it never really gone above 300. And we are now way above that, 425 is the latest. So we've dramatically increased it. From the last ice age, that change occurred over 5,000 years to bring us back to the weather we're living under now, 5,000 years, that change in carbon dioxide has occurred in less than 100. Okay, so we're talking about really, that's why it's so steep on this plot. Methane and same. So we know that these greenhouse gases, especially these top two, carbon dioxide and methane, the nitrous oxide plot looks just like this as well. The only one that doesn't look like this is the fluorine ones, because they weren't around until about 50 years ago. So all of a sudden, we just got a little bit of a thing going up there. So the greenhouse gases are increasing. Now I should say one thing about water vapor. Now, water vapor is water as a gas. You can't see it. You don't know it's there. You can feel it. And if you think you see water vapor, you're seeing water vapor that is condensed. So it looks like steam or fog or clouds or whatever. But water vapor you can't see. But water vapor is the primary greenhouse gas for the atmosphere. But it wasn't in our table. Totally omitted. How could we forget water of all things? Well, the reason for that is that water is condensable. So we have a certain amount in the atmosphere. And if you get your little camp stove out and boil water, get some more water vapor up in the atmosphere, you're not going to raise the temperature of the earth by doing that. You're just going to saturate the atmosphere with water vapor. It's all going to come back down as rain. So there's no way you can try to force more water into the atmosphere to raise the temperature. The amount of water in the atmosphere right now depends on the average temperature of the atmosphere. And as the average temperature of the atmosphere goes up, more water vapor goes into the atmosphere. So this relates, however, in a big way to the greenhouse effect. So as greenhouse gases start increasing in their amounts, that raises the temperature a little bit. That raise in temperature brings more water in, which raises it even more. So it's a positive feedback. And water amplifies the original effect of the gases. So it's critically important. It's just that you can't say, oh, carbon dioxide isn't important because water is the main thing. Well, yeah, but carbon dioxide is important because that's what allows water in the atmosphere to increase. Okay? So, that's why water isn't in the table. Now, energy balance, we're back to that. So we've seen carbon dioxide shooting up through the roof, methane shooting up, and even now our good modern technological society is pumping out all sorts of fluorinated compounds into the atmosphere, and that's causing the temperature to rise. And it's causing it to rise because the amount of cooling radiation going out has been blocked. So we have an energy imbalance then that's increasing as we go. And the energy coming in from the sun, which is roughly constant, we saw, is now greater than the energy going out. And so we have excess energy coming into the Earth system. It's got to go somewhere. Where does it go? It goes almost entirely into the world's oceans. 93% of that imbalance goes into the oceans. Now, it's a good thing for us that the oceans are capable of handling a lot of energy. I mean, they can take a tremendous amount without their temperature rising too much. In physics, we call that a heat sink. Okay? It's the massive heat sink of the planet. So our atmosphere, which is getting warmer and warmer all the time, we had our 3 hot days this last week, only absorbs 2% of that energy imbalance. Continents, including the biosphere, about 2%. All the rest goes into melting ice. Okay. So that's what happens when you have an energy imbalance. Now, the temperature will rise, and if we keep everything constant, don't put anything more in the atmosphere, temperature will rise to a new balance, and it will stay there. Now, there's plenty of evidence that there's an energy imbalance, because all of these are measured all the time, and they are all increasing all the time. The total heat content of the ocean, the sea surface temperatures, the temperature of the water right at the surface, that's much warmer than the total ocean. Temperature of the atmosphere. Ice is melting all over the place on Earth, all over the place, and sea levels are rising. Okay? So this is measurable indicators, measurable evidence of climate change. I just want to talk about a couple of these. So let's talk a little bit about this ocean heat content. That's really the biggest thing that people really want to get a handle on. And so I want to talk about a system called Argo. And Argo uses these wonderful little floats, these technological wonders. And these floats are programmed to descend at a certain rate down to about 1,000 meters deep, 3,000 feet deep. It's a long way down. And then they drift there for about 9 days, measuring temperature, measuring it on the way down. They also measure salinity. Then they drop down to 2,000 meters, 6,000 feet, over a mile deep. They measure temperature. Then they ascend. Then they beam their data, that's a lot of data now, to the satellite and then back to a receiver. And then all that data gets fed into very large computer systems for analysis. And how many of these are there? 4,000 in June of 2013, all over the world's oceans. These things are diving, coming up, diving, coming up, diving, coming up, measuring the temperature of the ocean down to 2,000 meters. Now the ocean in many spots goes way beyond 2,000 meters. Goes 5 miles down in some cases. And all of this data then is continually tabulated and analyzed, allowing me to make a plot that looks like this. This is the ocean heat content in the very strange unit of joules. So these are joules times 10 to the 22nd power. And from 2005, when Argo started, till just the last 3 months, we see a steady, unabated rise in input of heat into the world's oceans. And that amount of heat since 1998 is roughly equivalent to about 3.3 billion Hiroshima-level atomic bombs. That's the total amount of energy that's gone into the world's oceans. Okay? Now, that's a lot of heat, but the total ocean temperature got a little bit higher because the ocean can absorb tremendous amounts of heat. The surface has got much warmer than the abyssal depths. And they do send some probes down there periodically, and sure enough, the heat is even making its way down to the really deepest parts of the ocean. So that's one type of measurement that's made all the time, continuously, and analyzed. And again, it's unabated. Another one that's commonly used is measuring atmospheric temperatures. There's a number of ways to do that. One way, the simplest way, the good old-fashioned way, is to use little weather stations, little boxes that have a temperature measuring device and maybe linked now to the cloud. collect continuously temperature information. And they're all over the place. This just shows North America, and the highest concentration of these, nothing even close, is the US. Even Europe has a much higher concentration of these. But even way out here in some of these, in Greenland, there's temperature stations, not many. Okay, so these collect data, and these are collecting data over land. They're sitting on ground. They're not out in the middle of the ocean. They might be on an island in the ocean, but they're measuring temperature. And then all that data is fed in, and the computational methods here create grids that average out and combine these things and come up with a total global land temperature. Okay. Now, at the same time, satellites are orbiting the Earth, and they are continuously sampling the first 1 millimeter of the surface of the oceans, 1 millimeter down. And they're measuring what are called sea surface temperatures, SST. And then, so the land temperatures are combined with the sea surface temperatures to produce what's called a land-ocean global temperature. Okay. So it's averaging all sorts of stuff. The hot sands of the Sahara, the frozen tundra in Russia, whatever. They're all getting averaged together for a value. Now, there are other ways to do this. There are satellites that measure the temperature of the troposphere. That's easier. They just go around. And they are pretty much lockstep in their findings with what we get from the ground stations. But this was the first thing. These have been done, well over 100 years for this sort of thing. And then when you plot this, you see, first of all, a lot of noise bouncing all over the place. But for the last 50 years, it looks very much like the ocean temperatures, straight up, unabated. And this may not mean much to you, but the current 50-year rate of increase is about 1.8, 1.9 degrees centigrade per century. And that sort of thing doesn't maybe sound like a whole lot, but maybe when we're done we could talk a little bit about like what does a 1 degree change mean. Okay, but in both of these cases now, we're seeing this steady march of increasing heat into the system. Now, one other thing that's measured a lot is the melting of ice. And this graphic is pretty good because it shows us the types of ice on Earth. There's two major types. There's ice that floats on oceans. This is the Arctic. Okay? That's called sea ice. If all of that melted completely, the sea level of the world's oceans wouldn't change a bit because they're already in the oceans. They're already floating. Okay? However, the land ice is a different story. If that melts, then it runs into the sea and raises the sea level. And there's two types of land ice. There's glaciers found like in high mountain areas all over the world. And there are over 200,000 glaciers on the Earth. Then there are two major ice sheets, one in Greenland, one in Antarctica, not shown here. And these are thick. Greenland is up to 2 miles thick. Antarctica, 3 miles thick. That's a lot of ice. And between Greenland, South America, and Antarctica, that's 99% of all the ice on Earth. Okay. So, but the key point here is it's melting. And the melting, especially of these big ice sheets, is done by satellites that are able to measure gravity changes. So they can actually give pretty good estimates of the total mass of these ice sheets and how it changes, and the total mass of the glaciers. So a lot of measurement of ice melting because that's a fairly important thing and it's a fairly strong indicator of global warming. So here's an article from the Washington Post a couple of years ago. Earth is now losing 1.2 trillion tons of ice each year, and it's going to get worse, and it already has. Now the ice that's melting in 2021, the main amount of water is coming actually from the glaciers, because they're smaller, more susceptible to the temperature change. Then followed by Greenland, and then Antarctica. But the three combined, over 1.2 trillion tons of ice converted to water. And here's a Greenland melt stream flowing into what's called a moulin, and that goes all the way down to the base of the ice sheet. Might go down a mile, mile and a half. And then that water gets under the ice sheet. Now that, of course, land ice like this raises the sea level. So here are projections of sea level if it's just melting. These sort of projections don't take into account the possibility that a big chunk of the ice sheet will break off, which could happen, and float like a piece the size of Arizona or something floating out into the ocean. And then that will have a bigger effect on ocean. This is just melting. Okay? And it shows three different scenarios. One, we get greenhouse emissions down to zero, which seems highly unlikely by the year 2100. We stabilize them so they don't change anymore by 2100, or business as usual, the way we've been doing it. And over there on the axis, that's global mean sea level in meters. So with the high emission scenario, it's shooting for about 10, 12 feet by 2300. So these are dates well beyond what we're looking at here. But even by 2100, we're looking maybe at about 5 feet from just melting. Now, the other thing that climate change will affect is rainfall, both flooding and droughts. And here are projections for the time frame 2081 to 2100. So it's about 60 years from now. And what it's saying basically is that the areas that are dry now will tend to stay dry. So deserts, American West, Sahara area, Mediterranean, Australia, some parts of South America. But they'll get drier, 20% drier, maybe 30% drier, maybe in some areas 40% drier. And areas that have tended to be more rainy will get more rainy. And the reason is the higher temperatures will bring more evaporation to these areas, and the higher temperatures will hold more water in the atmosphere. So when it dumps a lot. So we look here at Pennsylvania and we say, not too bad. Not too bad. Anyway, so all of these things are I think increasingly strong. I'd say irresistibly strong evidence that global warming is continuing, and it's continuing due to the emission of things like carbon dioxide, methane, and now even threatened by these new fluorine-based chemicals. I'm not going to say too much about the impacts other than to put them up here. I was just talking with somebody about the heat in Texas and Arizona. I mean, intense heat, debilitating heat, and deadly heat. And these impacts now are things we're already seeing. We're not seeing them necessarily on a wide scale, but we're seeing them. When the glaciers melt, and it was glaciers that are melting the most, many of those glaciers melt to provide rivers. I don't know what happened here. Well, I think I'm gonna have to shut it down and start it up again. Yeah, many of these glaciers help produce rivers. The Himalayan glaciers, for example, provide water to China and India. That's a lot of people. Now, they're the least affected so far by climate change. But still, if you look 50 years down the road, there could be some serious problems if those glaciers are depleted. Let's see what I can do here. Okay, so then there's always the force quit. You don't see what I'm seeing. My thing is just clicking in. And it's saying, your time is up, time is up. So, with drought, yeah, why am I getting no signal? Well, we'll see it. Well, I'll just let that go. But the other things then are, that I had on that list are flooding, inland flooding, and coastal flooding due to different things. More powerful storms, more energy into the system, which is what continually happens, means stronger everything. All right, now I got something. But not on that. Let's just see if I can. Yeah. Okay, so I'm gonna stop that one. I don't know, it's something here, but that was my last slide. So, but these are the, another thing I wanted to mention is climate refugees. We're already starting to see that. And refugees are creating such animosity in the world. And the climate refugees are going to just double or triple that. And so I think it's, it's going to be increasingly a rough ride as we go through this. Now, next time I have talking about next.
What are climate refugees? I don't know that term.
Okay, so you would hit, for example, one area where that's occurring right now is Bangladesh, which its average height above sea level is not very big, 20 feet. And a lot of the lowlands now have flooded. And the people, the farmers that are living there now, they're refugees from that area, but they're crowding the big cities in Bangladesh. But a lot of the Syrian refugees that we had several years ago, that was sort of mixed in with not only the war, but the drought in Syria. So there wasn't food, there was war. And so people will be fleeing areas where there are real climate issues. Probably the biggest one will be agriculture. That the area used to growing a certain type of food now is no longer suitable for that. And the transition is hard to make if people are starving, and they'll be. So I mean, those are possibilities.
The Canadian fires are massive, as we know. The smoke's even reaching Spain
Yeah.
What effect does that have? There's supposed to have been like 500 fires going on, and of course it affected our climate here. What all happens in something like that?
Well, the one thing, the amount of heat produced by the fires doesn't really affect the global temperature much. Same thing is true of volcanoes. You think, wow, all that heat coming out, but that's just a drop in the bucket compared to what the sun's bringing down. But the Canadian fires will produce particles that will find their way up into the atmosphere and exist for a certain time. And then they will actually block some of the sunlight coming in. So both volcanoes and forest fires like that can have a temporary cooling effect. But the health effects are major.
Yeah, what I read an article one time that was talking about the effect of Mount St. Helens in terms of reducing global temperature. And at least they claim to have a measurable effect upon global temperature. There was also an experiment run by Gates, in which case he was dumping, I believe it was lime, basically, calcium compound, into the high atmosphere directly from aircraft. For the same concept, if we put enough white shield up there, you reduce the absorption that the other gases are getting, so you can reduce the global temperature by dumping enough white into the higher atmosphere. I just don't know whether that has any support in the scientific community.
Yeah. Yeah, and it would depend on how long it could stay suspended up
Yeah.
there.
Yeah.
But one of the effects that is starting to be seen is that part of the increasing temperatures now are due to the fact that we've been so effective at scrubbing sulfur compounds out of the coal power plants. And so therefore, they used to produce sulfur dioxide, sulfur trioxide gas, got to go up in the atmosphere. We combined very tiny droplets called sulfate aerosols, and they would persist in the upper atmosphere and they would reflect light from the sun. And now that's not occurring nearly as much. And so there's a heating effect from being environmentally sound. Another thing, earlier this summer in May and June, there were, I guess, some powerful Saharan winds that lifted very fine dust and it drifted north and it shielded Europe. Europe was cool for some of those early months. They don't persist forever in the atmosphere. But yeah, so I mean, that's the whole, for a lot of people that model climate, that's the whole, that's the really tricky part, is to try and figure out how those things that reflect sunlight, and clouds also reflect sunlight during the day, and at night they hold heat in, so they have a double effect. And so when you're trying to predict or model things, it gets pretty complicated. And yeah, and you can, so the ozone, we all remember the ozone hole. Yeah. So that was caused by chlorofluorocarbons. Now they have been entirely replaced by fluorocarbons. And they both were greenhouse gases. But the fluorocarbons appear to be more potent. So in protecting the ozone, they're increasing the, so a lot of things are linked. It's not a simple situation. And yeah.
In your conversation, you sound like, which is interesting because the press seems to be focused on CO2 levels, and the but you sound like fluorocarbons are a bigger threat than
I think they're a potential long-term threat. So they have circuit breakers, big grid-level circuit breakers that have like 2,000 pounds of sulfur hexafluoride in there because it's a really good insulator for high voltages. Well, any leakage from there, you know, and a lot of third world countries are putting these in. Are they going to maintain them? Are they going to, you know what I mean? It's
Yep.
just, you really don't, it's sort of a wild card. You really don't know. But because they're such powerful greenhouse gases, it could be, and because of the fact that like sulfur hexafluoride, it's in the atmosphere 10,000 years.
so it doesn't biodegrade.
No, the reason it's a good insulator is it's so stable.
Yeah.
It can be under a high voltage and it's so stable. Now it gets up in the atmosphere and it's so stable. And nothing's gonna happen to it. Yeah, so I mean, that is a threat.
I'm confused. You mentioned about cleaning sulfur dioxide out of the atmosphere.
Yeah.
Ended up not being as good as we thought it was.
Oh, it's very good. Prevents acid rain, protects lakes, forests. It's just that it also reduces the sulfate aerosols that had existed for many years, and they reflected. They go up to the stratosphere level, and they're stable up there for quite a while, and they reflect sunlight back. So when you scrub the sulfur dioxide, then you're saving the lakes, saving the forests, and letting more light energy in.
You're saving the lakes and we're burning as a result of it.
But that was one of the interesting aspects of Bill Gates' experiment with lime, because acid rain still is a problem for us. Basically, putting lime into the atmosphere ends up with a neutralizing factor there for that, and the white helps reflect.
Yeah.
So it's an interesting experiment which it got announced once and then disappeared from the press, and since I don't follow those things, I don't know where that stands.
It's the old adage of cause and effect. We do something, we don't know the effects until later, 30 years later or 40 years later, and then we go, oh, maybe we shouldn't have done that, we should have done this. We're always behind the curve.
We always are.
Okay.
We talk about climate change affecting our weather. El Nino is supposed to affect our weather. Is there a relationship between the two things?
Well, El Nino occurs when it's an oscillation, the El Nino. And what happens is in El Nino, a band of surface water, maybe 10, 20, 30 feet deep, spreads from South America all the way across to the Indian Ocean, across the Pacific in the equatorial region. So you got this really red, when you look on maps, red is warmer. You got this really red band going across the equator. And then that's very effective then at transferring that surface water heat to the atmosphere. So when you have an El Nino, and that may last for a year, year and a half, then there's a lot of heat transfer from there up to the atmosphere. And the temperatures rise, there's like a month lag or something, and then they start rising. But then it oscillates. Then all of a sudden, really deep water bubbles up along the coast of South America and spreads out over that same area, and then all of a sudden you got a blue band, a cooler band, and then that sucks heat back into the ocean. So it's, but as it gets warmer and warmer, then the net effect. But the warming itself isn't really associated with El Nino. But El Nino always produces a spike in temperature. And what the warming has done is to raise the baseline. So now the spike earlier, now the spike now. Yeah, there's an El Nino start now. We've had the cool phase is called La Nina, which is the little girl, and El Nino is the little boy. Little boy is more troublesome than the girl.
Far too true.
But, so we're looking now in the next year at seeing at least a temporary elevation in atmospheric temperatures, because we're going to get a net transfer from ocean to atmosphere.
Your land temperature plot showed this slope going up. Early 1970s, it was oscillating. There was kind of a small trend, it was going to go up and then it started to take off.
Yeah.
It's, obviously all of this has been coming for a long time. Is there any indication what that was due to, that change in slope was due to in the 70s? Is that the scrubbing of the sulfur compounds out of emissions? Because that seems like that would have started back early.
Yeah, there are fluctuations, and the total greenhouse effect that was expected to emerge from the noise around late 90s, early 2000s. So there's a lot of noise in the system, and if you don't have a strong effect, then it's hard to tell, what some of those things. In the 30s and 40s, the Dust Bowl, we had a big spike in temperature. In the 60s, it cooled down again, and everybody was saying, temperature is cooling. But then after the 70s and early 70s, it started going up. But now it's well beyond the noise, the global warming signal. Much more than noise.
In the 60s, I remember talks of an ice age, but that was, only those of us of that age know that.
Some people brought up the ice age thing.
Yeah.
So next week I'll be talking about what are the strategies for dealing with this problem going forward.
Okay. Thank you.
Yeah.
Thank you.
It'll be interesting.
Yeah.
I don't think I'll be around to see the effects.
I don't know if this thing is on a timer or.
I'll stop on my grass for a while.
Lots of things to take home. Seems meaning of life.